Our second example is the second, well, it's probably equally as common as the first example. The first example, we created a polar integral. The second example, we're being given an integral in rectangular coordinates and we want to convert the polar. Now, what do we need to do? We need to draw the region. Why do we need to draw the region? Because we need to draw rays instead of lines. I see that y starts at 0 and ends at 2x, right? I see that x goes from 0 to 1. They go like this, like this. This is 1, and this is 2, like that. Good. Now, how do we convert to polar? I know it's going to be a double integral. I know instead of dy dx, I have r dr d theta. And I don't want to stress this enough. I don't think I can stress this enough. That dy dx is not equal to r dr d theta. Is when we actually made the French fries with polar, with rectangular, we had to use delta y delta x for the base of the French fry. When we made polar French fries, the area of the base is actually r delta theta. All right, that's not so bad. We know it has to have all that. I know the roof's equation needs to change, but that's not so bad. Y is r sine theta. X is r cosine theta. And if we were going to actually evaluate that, we just cancel the r's and make that tangent. That's not so bad. We now need to find the limits of integration. Well, how do we find the limits of integration? We start drawing rays. And we want to know what is r as those rays enter the region. Well, they all enter the region at 0. So that's a gimme. They all leave the region when x equals 1. Now the problem is that doesn't put a 1 up here. X equals 1, not r. I need to look at my x equals equation and find r. Well, how do I do that? X is r cosine theta. And now I solve for r, which we can rewrite as secant theta. We don't have to. Really, it's just what you're more comfortable with. This needs to be secant theta, like that. And now we have to ask ourselves, what thetas was I using as I was drawing all those rays? Well, the smallest theta I can use and draw a ray that hits the region is when theta equals 0. That's great. The biggest theta can be is whatever theta is up at this point right here. Now, we know that the height here is 2. We know that the distance along the side is 1. Right, so the biggest possible theta, I'll call it theta max. I'm not always going to include the max, but this is just so when you see it, you can see this. It's going to be, well, what do I know? It's going to be the arctangent of 2 over 1. And that's just the arctangent of 2. And that's going to go right here. And that's how you convert a rectangular integral to polar. You need to sketch the region. You need to replace dy dx by r dr d theta. You need to find the equation of the roof in polar. And then with the region, you have to start drawing rays and ask yourself, what is r as those rays enter the region? What is r as those rays leave the region? In this particular integral, I think this integral just got harder. But there are many, many integrals that become much, much easier when they convert to polar. I don't know if you're aware of this or not. But polar coordinates were in part invented by Isaac Newton to solve problems. He actually, as I'm told, invented 7 different coordinate systems to solve the problems, and polar just happened to be one of them, and we find it particularly useful for things in like statistics or engineering or physics.